Right, so I look at some of these papers, which we'll look at together, and I distribute on the Cebeci-Smith model. It was really, I think, mainly brought forward by Tuncer Cebeci, and he's actually a Turkish guy, and I found this photo of him up here at the top, and he actually passed away in March of 2021, which is too bad. And this model had a few major impacts, which we see flying today. Once I noticed the F-18, and the other is F-15. Obviously, they use the non-axisymmetric form of the model, but these are more contemporary, flight vehicles that are still flying today, but they were designed way back then with his work. So since it's here, a lot of this is just about birth, where he's from. You can read that. Since this is a technical class, let's focus on some of this where he went technically. But he went through the university system in the United States out of Turkey, and he joined Douglas Aircraft Company as a research scientist, became the head of aerodynamics research in '74, and he became a technical fellow. And a lot of these aerospace airframers have positions called technical fellows, and if you work hard, you can be named one, which is pretty cool. And he won a bunch of awards through AIAA. This one's still given today, basically Fluid Dynamics Award. And then he became a professor at Cal State University in Long Beach, and they have, I think, an aeronautics or aerospace department there. And he was the founding member and chair of it. So he had a pretty nice career. Another reason I think that the United States should seek out and bring in really smart people for the benefit of our country. And this was actually published in the official, I guess, obituary that his family published not long ago. Hopefully it wasn't a COVID death. Technically, let's focus on maybe where these codes were run originally and why some of the choices were made for algebraic models. And this is an IBM 360. And a lot of these old IBM 360 models were running Fortran. Excuse me. And if you look up these model numbers, they have a little slash, and they might have something like a 65. Usually that has something to do with the number of processors in it. So they had 65 single core, in today's terminology, processors. And these things were not cheap, as you can imagine. This is the order of the height of a person, and consumers couldn't find them. And I mean, even today, it's hard to find a consumer machine at 64 processors approximately. So that's the type of computers he was running at. These are pictured in like the Computer History Museum out in California. So let's look at two of his papers, and I think what you'll see in these papers is just a few interesting notes I want to point out, and you'll see some of the exact same equations written that we covered in the previous two classes, which were on Tuesday. So in this one's a more of a theoretical paper where he outlined the method, and it's basically he's taking the equations and he's modifying the Van Driest model to have pressure gradients and mass flow rates, and heat transfer model for eddy conduction coefficient, and putting it all together and showing some results. But he's not talking about the implementation at all. The second paper I show today will talk a little bit more about the implementation with his co-author Smith. So here, single author article, and it's pretty difficult to write a single author article because everything in there is his work, so he doesn't have any co-authors to rely on. And I always encourage everybody to try and write at least one single author article in your career, because that way you have something to kind of say is totally yours. Nobody can take that away from you, which I think is nice. So let's just kind of like look at a few important things in this paper. And I always read the abstracts first, and there's one, of course, important point that this model for the experiments they looked at is a valid range of Mach 0, which wasn't a flow at all, so that's an odd thing to say, but maybe very low speed flow, incompressible low speed boundary layer, all the way up to Mach 6.7, which is a hypersonic range, which is an incredible range for a turbulence model to be validated over. And it ran really fast. because it's an algebraic model with little modification. In this paper even, it's hard to like dissect the model and see which equations are like supporting equations and which ones actually went into the code. And I find like the second paper to be much more useful for like saying, oh, I want to repeat the model, because he just lists the equations, which we would go in code. So let's look at this. Typical paper, he's got all his nice, in AIAA, they have all the nomenclature right away, which is great, so I can go back and refer to it. And I love it in papers when people say right away what they're going to be doing, so I don't have to read a long, lengthy introduction like a review paper and figure that out. And he's very quantitative. For example, he's looking at experiments over ranges of Mach 5, looking at different experimental values. He actually lists them instead of saying it. And then there's a bottom line of saying there's sort of a 3.5% changes. Other things I like, he's just saying this is some of the major advantages of his model right here. You say there's one eddy viscosity formulation, one turbulent Prandtl number, and I believe in this paper somewhere he says that there's only 4 coefficients that have to be calibrated. In the turbulence modeling world, I think it's something to be bragging about to have less coefficients, because it shows that you have less terms to calibrate to match a wide range of experiments. And so if you have a small number of terms, but a wide range of experiments from a lot of different authors, that's powerful. Because even if you run the same experiment at 2 different wind tunnels, they often give slightly different results just because the facilities are different. So having a wide range of values over a wide range of wind tunnels and capturing a lot of that data gives a lot of impact and power for a model to be accepted. And if you look at the turbulence modeling resources of NASA Langley, I think it's really interesting because they collect data from multiple experiments. And one of the criteria for a model to be kind of accepted and validated is its implementation in different CFD codes. Just like we would do same flows in different experimental facilities and get slightly different results, if we take the same turbulence model and put it in different CFD codes, we also get slightly different results. So taking a turbulence model and have it implemented in different CFD codes is also powerful. Right in here, this section, I love that right away he puts his assumptions. So he says, you know, what is the capability of the model in terms of experimental error? And then right in here, he's talking about some of the assumptions in the paper, which I think is really important to lay them out. You shouldn't be putting down prediction models without those assumptions. Like every good paper, he repeats the equations, the governing equations that we're solving, and we've seen these in class many times in a few different forms: continuity, momentum, energy, and here's the boundary conditions for the particular problem for mass, momentum, and energy in 4 and 5. So you see that there's some mass flow condition if he has blowing or suction through a wall, like on many aerospace devices for stability, and he has something about the edge. So he's really only solving for the flow and the boundary layer. He's not doing anything outside the flow and the boundary layer over these vehicles. So those are the equations. He's already done all the averaging and everything for you. Let's all assume that you know that. And right away he says here's the closures for U prime V prime and V prime H prime, and H is total enthalpy. He defines a turbulent Prandtl number, which he sets as a constant later as 0.90 for these flows. And then he describes an inner and outer viscosity model. And this is probably one of the biggest problems with, or criticisms, I would say, of Cebeci's model, is that this term here really is some property of the boundary layer. And this term here, of course, is some sort of length scale model L. So right there it's algebraic because he's specifying 2 things really about the boundary layer. He's tracking like boundary layer displacement thickness through the flow, and he's tracking a length scale explicitly. But I mean, you should expect at least one of those in an algebraic model. And up here, he also includes intermittency, and we've talked about this exact factor back I think way back when we were talking about physics of boundulars in the class, right? So there's some factor from 0 to 1 for intermittency. So it's also been included. Now, he's taken all that, and just like in the previous class, we talked about Van Dries, model, and how that's modified to handle flows with strong pressure gradients and blowing and suction. Okay, and so he's going through this, and he writes in this section, we'll generalize the Van Dries expression, and that's kind of what I showed in the previous class. And he talks once again about the Stokes flow solution. So here's this boundary condition, and he makes a little transform, and he finds the analytical solution, which we found in the last class. So that equation should look familiar, but it's never used. And if you scroll down, you'll see that there's this factor here, and he modifies the Reynolds stress model with this same factor to capture the decay of shear waves away from the wall. So that's all stuff that we've looked at. And then he comes up with this modified closure equation. So compare 22 with, say, number 9. And you can see it's a little bit different, isn't it? Anyway, modified values of m. And then these things here are mostly arguments like we've made in the previous class. You'll see they're not going into the final equations. And he modifies that value of a here, which goes way back into your model back in the beginning. And that'll be way more apparent in the other paper. And so when I like to take someone else's model, they usually have a theoretical paper which I study over and over and over again, because every time I read it, I'll learn something new. And then I look at like an implementation paper like the one we're going to look at next. And they usually just talk about the grid, the algorithm, and how they implement it, because that's very important in terms of repeating others' work. So in this paper, he's kind of laid down his equations and arguments, but he doesn't talk at all about how he solves them numerically. But he does show results. And like I mentioned just now, the results are from a wide range of experiments. So I always say, with the students I work with, how do we know this is right? How this is known this is validated? You got to compare it against something. It could be an analytical solution, but in this case, it's experiments. So here's 2, and the first 2 are basically Mach number profiles. So the x-axis is the distance from the wall in a turbulent boundary layer, and the y-axis is basically normalized Mach number. And the graph is a little bit tricky, because you can see in this case, this is some distance down, and the value is 1, and the distance here is 1 on the same axis. So this is really a multi-axis graph. He just normalized it with an offset to make it more prevalent. So in these experiments by Michael, they're the dots, and it's sort of just plotted in outer coordinates, and it captures sort of these nice straight regions that you'll see in turbulent flows. So that's just one set, and you can see those Mach numbers are 2.57. TW is the temperature at the wall, TE is the temperature at the edge, so there's a large temperature difference in the flow. Right away, second graph. He compares it to a different experimental measurement paper of boundary layers, this one by Pappas and referenced, and this time he plots the data a little bit differently, but normalized with theta, and just to make sure, theta is your momentum thickness. So here's the wall, right, and there's your unity value, and there's the same Mach number, and this time he collapsed the data. Here's 1. Just his choice. I guess if I was a reviewer of the paper, I would probably say, why is it in figure 1 you've done it this way, and in figure 2 you've normalized it with a different way. That's a little bit strange to me, but there's never a perfect paper. And you can see the collapse of data all over a number of predictions with this method. So 2 different experiments, multiple Mach numbers, Reynolds numbers, temperature ratios are all predicting the mean flow and probably temperature profiles correctly, because Mach number, right, goes as u over the square root of gamma RT, roughly, in the boundary layer. Anyway, let's just go down and look at a few other interesting results in the time we have. These are skin friction graphs and Stanton number graphs. ST is not Struhl number, it's Stanton number. It's non-dimensional heat transfer rate. And CF is skin friction. So these types of graphs, skin friction a little bit harder to measure. experimentally than just say the velocity distributions. And so these things are just decaying, and it's harder to get better agreement with that. But you can see here's the Mach numbers, same experiment by Pappas. So just going down, looking at different graphs just to look at them. Here's calculated experimental velocity and Mach profiles for another boundary layer, Winkler and Shaw. So there's 3 experiments so far. This one has a direct velocity measurement and Mach number. Now you can see this comparison is not as good as the previous ones, still normalized by a thickness. And in this region here, you can see there's starting to get appreciable error. But you see now that edge Mach number is 5.21. And it's also a little bit lower Reynolds number, meaning it's closer to the front end of the plate. So usually, remember, these models and our assumptions for their formulation were for high Reynolds number flows. So if you have a boundary layer in a wind tunnel, at some point the boundary layer starts, and your Reynolds number is dependent on the distance downstream from the leading edge. So some of these turbulence models, when you make high Reynolds number assumptions, like all the popular ones, they don't always do well in that region, a transitional region or region near the leading edge, because we haven't talked at all about transition or anything. Let's look at a few other cases. So here's a little bit better case. This is 5.29 temperature wall over the temperature of the edge of the profile is almost 6, and there's better agreement. And why? Higher Reynolds number. Right there, RE theta 4300. So let's see, that's about only another, yeah, I guess it's double than the previous case. So all they've really done is move their probes experimentally downstream. I got a high Reynolds number on the plate, and you can see that difference in the inner layer near the wall has gone down. And so you would actually expect the farther downstream you go with this model, the turbulence becomes more fully developed, farther away from transition, higher Reynolds number, and your velocity and experimental, or your predictions and experiments will agree better. These are the same types of plots. Non-dimensional heat transfer, skin friction, which is non-dimensional shear stress. They all have the same trend with increasing RE theta of going slightly down in that direction. They both follow the same trend in general boundary layers. And I should mention all those experiments were flat plate experiments. Let's go down more, and you can see he's showing a whole nother data set, all these same type of measurements, and he's tracking boundary layer parameters, displacement, momentum thickness, heat transfer, with a totally different experiment and data set. Here's the velocity profiles, and I should mention this flow is a little bit different because there's some curvature in it, and it's actually accelerating, which is a more difficult case to capture. And that means there's some pressure gradient in the flow. So the previous cases didn't really have strong pressure gradient. Now you choose an experiment with some acceleration and pressure gradient. And you can see just from looking at the results that his predictions with experiment, it would hard to do a better job. One thing that you'll also notice in this paper is that there's no error bars on the experiment. And look at the date of the article. This is in the 1970s era. And it used to be a requirement for aerospace journals for experimentalists to publish error bars. So I would expect to see like a little error bar like this around each graph. And that way I would say, well, if my prediction goes to the error bar, I'm happy. So since there's no error bars here, it's really hard to know if he's within the experimental uncertainty. If you sat down and read this paper, you'll also notice that for every set of figures, there's an excellent discussion. And he often describes the experiment in detail and if it might violate his assumptions of the model or not, and also give you quantitative information about the differences between the predictions and experiment. So that's the analysis. So I think if you want to sit down and see how someone pretty smart who came up with a model like this thought, it might be worth doing. Just looking at a few other quick ones. Here's some work by Squire. I think this might have been an English theoretician who did some experiments too. And, they kind of follow the same trend, so I don't want to just keep looking at the same data over and over. But this is what's strong about this paper, like I said, is you're starting to get the idea like, okay, I took my model and I applied it. I calibrated the coefficients once, the 4 coefficients, and I ran it against all these different flows, and I'm getting pretty good predictions. for accelerating flows, pressure gradients, mass flow rates, and it's a very robust and quick model, and it would run on a single IBM 360 series computer, you know, and but then you said, well, how fast is that, and how fast would that be today? Well, if you ran this on a single processor, like on your cell phones, on your desks in this classroom, you know, you would run it by hitting, say, maybe run, if you can make it into a cell phone app, and it would be done by the time you release your finger. So the amount of computer power today to evaluate a model like this over a full aircraft is like nothing. And but back then it might take on the order of minutes. So let's look at the second paper. And this paper has a totally different flavor, and it's written for a different journal. This AAA journal doesn't, I guess back then at least, typically put out papers like this, so they sent it to American Society of Mechanical Engineering. Another thing about these types of journals is sometimes it's good to publish your work in different journals, because that way, if you want your model to be adapted, it's a good strategy for a wider audience to see it. So that's another little tidbit of information for those of you in this business. So let's look at this abstract. This abstract's a little bit different. This first part of it, in a 2-paragraph abstract, talks about basically the qualities of the model. What is it? Eddy viscosity. There's a composite layer consisting of 2 sections of eddy viscosity, and uses a single Prandtl number. So in these few sentences, he said what he's done. And then this is really about programming and evaluating and benchmarking. So then he talks about the computer and the outcome and the amount of time of the solution. So here's your IBM 360-65 machine, which I showed a picture of the machine up just a few minutes ago. And he worked really hard for incompressible flows. He says it's only taking about 2 to 3 seconds for a typical flat plate flow. That's pretty amazing, because in the class that I teach, Introduction to CFD, for seniors in aerospace, we use a code called SU2 here in the year 2022, and we might run that code on a flat plate boundary layer using the same number of grid points as Cebeci and Smith. And so we're solving the full Navier-Stokes-Rand-based equation with a 2-equation turbulence model. And some students, you know, when they set up their grid and code, it might take a couple hours to finish. Some might take 15 or 20 minutes if they have choose, you know, kind of optimal numerical algorithms. So solving the full Rand's equations with a 2-equation model on a modern laptop in 2022 might take, you know, on the order of an hour. And this is 1970s, so that's 50 years ago. He's doing the same problem and getting essentially the same solution in seconds, albeit on a much less powerful machine. I think that's kind of interesting to think about in hindsight. So there's a power for algebraic models still, if you're doing large problems and you want results really fast. Now there's some things in this article I just kind of want to circle and point out, which motivates the third computer project. And part of that, of course, is grid stretching. And he has a nomenclature section here. And this paper opens just very much like his previous one. And he's already talking about the validity. Mach numbers up to 5. Previous paper, he had a different number. And he has examined 43 experimental values, and there's particular numerical techniques. He's getting 3.5% error, which isn't bad. And he goes down here and says this is where he's talking about finite difference approximations and using grid stretching. So this is what we'll be doing in the third computer project, really, applying boundary layer equations with grid stretching for incompressible flow. So he's shown his governing equations again, counting momentum energy. So we've seen these, and remember, this is a little r to the k value. He just sets k equals 0 for 2D flow, k equals 1 for axisymmetric, and he's interested in axisymmetric problems. So we go down here. This is I can't remember if this is the same figure or a modified figure, and he casts his whole equations where this is x equals 0, and then this is the x direction, and then this is y, and he's shown basic velocity profiles and enthalpy profiles. And really his geometry for these types of problems for a simplified solver is where you basically have the surface defined as a value of x and r naught. And that's really his geometry. His geometry is only two columns of numbers, x and r naught, and he would build a grid around it. So the grid might look something like this. That. And then he used grid stretching, so most of his grid points are located near the wall, like this, and they get larger and larger as you go away from the wall. And that's a good strategy when you're doing boundary layer flows. And he would have to transform this grid in x and r coordinates, or x and y coordinates, into Cebeci and eta. And that's shown in this paper too. But before he does that, he goes back and he shows his closure models. So he's really solving these set of equations, but they're not closed. There's extra unknowns. And this is where he goes in and closes his models. So you see you have a inner eddy viscosity. You have a length scale model, and we know y, that's the distance to the wall. We don't know a. That comes from the modified Van Dries model right here. And if you go up, he has the intermittency equation, just like his past paper. And then here is the other important outer model. He has a non-dimensional pressure gradient and the inner coordinate distance from the wall. This is the inner viscosity. You can see here's where A plus goes in. So if you just take equations 1, 2, 3, 10, 9, 8, the pressure gradient equation, and equation 7c, I think you have all the equations you need. And then you just have to calibrate 4 coefficients, which he lists somewhere in the paper. I think I've lost them in my notes. But they're not too important, because you just set them as constants in your code, and you run. But that's terribly inefficient, right? So he needs to transform his equations from like this physical space to the computational space with grid stretching, so have a lot of grid points near the wall. Otherwise, it wouldn't be able to even solve the problem in his large IBM 360 machine. So this is what we also looked at. So he uses the transformation to change his grid from grid point spacing dx to d Cebeci and dy to d eta. And so the grid for, say, Cebeci, if I can write it down here in the margin maybe, right? That's just a uniform grid now. And so you have like, this is delta Cebeci, and then this is delta eta. And when we talk about the third computer project, we'll talk much more in depth about this transform. So we're not going to use one this complicated, we'll use one simpler. I mentioned he solves it for a stream function, and when he does all that work, he can recast his equations 1 to 3, that is the momentum equation, equation 2, and energy equation, equation 3, in this form. And just like I mentioned the advantage of the last time, this model is decoupled. So at every station, as you're marching downstream, he used a marching method, just like we will in Computer Project 3. He would solve equation 13 for F, and then he would solve equation 14 for the energy, for G, and recover his field variables on the grid points. That's all nice, but he also had to discretize it and solve it in an algebraic solver, just like you're doing. And this is all kind of details about those two equations I just looked at. And he finally gets into the method of solution of the equations he's cast. So he's done nothing numerical up to this point in the flow, or code, excuse me. And then he talks about the discretization. So here's the graph I just showed of Cebeci and eta. And what would happen is he's starting at this location, marching downstream. So this is your streamwise direction, right? And this is your distance from wall. And he would discretize his equations using, excuse me, what looks like a T. At least that's the kind of like slang, this T discretization. So if he's at, say, point, I don't know, this point here, you can almost imagine that these points here would come down as you march downstream. So this is like the computational stencil. these are what are known as like the indexes, your index n, for instance, and you're kind of marching in the streamlined direction. So these are the locations and nodes on the grid corresponding to the discretized solution or equations to find a numerical solution. So we'll look at that a little bit more detail in our simplified solver to really understand that, because you'll have your own stencil, which would be one in our project will be like 3 like this, Craig Nicholson. Anyway, you have to start all this, and it's usually good to start from a condition, which is a valid solution. So sometimes he would just use a uniform profile. Like if you're at the leading edge of a flat plate, you would just set the initial solution to be the initial velocity. A better solution, which is more physical, would be to set the solution to a laminar profile by solving Boussinesq equation. So he could just set a laminar profile by solving Boussinesq equation and putting that at the leading edge, for example, of his vehicle. And that would be okay, I guess. And then you would say, well, how do I let the flow transition from a laminar flow to a turbulent flow with the same code? Because his code is not really a laminar flow solver. Now, if I set the eddy viscosities to 0, like if I go in my code and just say eddy viscosity inner and outer equals 0, the whole code reduces to a laminar flow solver. So using that like little trick, how could he like do a flow over a nose cone of an F18, which is pretty close to axisymmetric, and kind of simulate transition? What would he do?
Ramp up the eddy viscosity?
That's a good suggestion, is ramp up the eddy viscosity. But remember, the eddy viscosity is also a variable. So that's absolutely true. But then you also, again, are posing something about the solution. You would say, well, I'm going to let the eddy viscosity maybe be penalized by a function that goes from 0 to 1 in some certain range. That would certainly be something that gives you a solution. And it's actually probably a better solution than the one they did. It's more physical. All they did is just say, we're going to impose the eddy viscosity to be 0 over a certain length of the cone, where transition up to the point of transition. And at the point of transition, then we're going to take away the constraint that eddy viscosity is 0. And then they let the code naturally change the eddy viscosity from the transition point downstream. But that was a really good idea. I guess it does, I guess the good thing is like you're letting it slowly ramp up with some kind of function that you assume, which is another empirical turbulence model for transition. I guess the bad thing is you're not letting the equations do it. It's always better to try and let the equations let things naturally evolve. So I don't know if there's an easy answer for the question I pose, but it's a pretty insightful idea. I love it when these papers have flowcharts because a picture is worth 1,000 words. Here's the flowchart. I often make flowcharts in my codes to explain it to others. And this is just how basically the code runs. You basically initialize it, set up your conditions, you solve your initial momentum energy equations, and then you go over a loop where you march downstream to the next value at n+1. And he has like a little inner loop convergence for each step. So that's, the flowchart maybe isn't as detailed as I like in this paper because it doesn't relate to any equations or parts of the algorithm. And you can almost use the same type of flowchart for any flow solver in, like a 30-year period. So it's a bit general, but if you've never programmed it, I think, or kind of gone through a code like that, then that's pretty helpful. A lot of the rest of this paper is benchmarking the numerics. And that's what a lot of these graphs are. He's actually plotting solutions with different grid point spacing. So you can see he's decreasing grid point spacing, and hopefully the solutions are converging. And back then, it was very expensive to run double precision solvers versus single precision, but they had control over that. They could do one or the other. And he was also comparing with grid point spacing changes in the y direction. How does single versus double precision affect the solutions. And you can see running double precision in a second, meaning you have, of course, more precision in your calculations or using more memory, actually changes, they could really diverge, I suppose. Anyway, that's not what I want to concentrate on. The last thing I want to point out in this paper, which I personally enjoyed, it is the benchmarking, because I used to do some benchmarking work on machines in my 20s. And he basically has different cases, and he has number of points, and this should be the number of points in the y direction, and this is the number of points in the x direction. And you can see a grid might be the total number of grid points. You would just multiply through 240 times 200, or 120 times 200, and that's the number of grid points in the grid. This is the number of grid points, this is the wall, and this is x, y, and there's your boundary layer profile. So this is really his discretization. And remember, most of these grid points in the x direction are evenly distributed. And so if you have a profile which is not changing much, and you have only a mild pressure gradient, you can get away with really accurate solutions with only a few points in the x direction. 14, that's tiny. And the other good thing about that is, of course, you have way less memory, and you can use higher precision. And if you have an implicit method, your code is more likely to be stable. So those are all good choices. And so those who pay the bills, because supercomputers are not cheap. You're paying for power and people and insurance and time, and you got to replace them every 5 years. So after 5 years, a supercomputer usually needs to be replaced. That's another $30 to $50 million bill. It's better to use less computer time. Anyway, most of the grid points in the y direction are down in here, where the high shear of the boundary layers, because of the grid stretching. And you'll see that in Computer Project 3. So these are all like the grid metrics, and here's the different cases studied. They're all referenced in the paper. They're not too important. What is important is down here, and you can see this is like the double and single precision columns. As you go from single to double precision in Fortran, for instance, you're just using more time. And this is computation time in minutes. 240 by 200 is a typical boundary, two-dimensional or axisymmetric boundary layer calculation today. It hasn't changed. So the number of grid points hasn't changed. You don't need more grid points. That's the power of Rand's modeling. The shortcoming is you don't get like temporal data, for instance, usually. And you can see in the 1970s, you got good solutions on the order of 3 to 4 minutes. Using the same grid, using general CFD solver, it's going to be a lot more. So that's interesting. Anyway, I think that's kind of what the main important things I wanted to point out about the articles. A lot of this other stuff is studying separation models and things like that and the numerics of them. I don't want to use our class time to get into that. So that's the end of what I want to say about the Cebeci-Smith model. And there are shortcomings. It's algebraic. And the biggest criticism, again, is that he had to know or specify length scales. But more importantly, in his model, he had to know something and track the boundary layer thickness and momentum thickness as the model marches downstream. That was seen as the biggest problem. And this is where the other people working on algebraic models saw an opportunity to make it more physical and just as fast and eliminate the need to track things like boundary layer thickness and momentum thickness and only track and say something about the length scale as a function of distance to the wall. And that's what we'll talk about Monday, and is also the basis of the third computer project. So thanks, and have a great weekend.
How sensitive are these, like in